Welcome. We will continue with response surface methodology. In this half an hour to 40 minutes of lecture, I will explain first order model with an example. So, if you recall my last lecture on response surface methodology, there I have introduced these two figures as well as this first order model. Also, I told you that what is the path of steepest ascent and the purpose of conducting first order model is to find out the path of improvement. Okay. Means if you are operating here, then here you conduct experiment and then obtain a first order response surface, and then using that first order model find out the direction of improvement, so that you can conduct sequential experimentation and finally reach to the region of optimum. I also discussed that when you go for first order response surface model, the contour plot for the responses will be parallel lines, and if you are operating here, then you start with the origin of this operating zone and then follow the path normal to the fitted surface. Also, I told you that in order to conduct the sequential experimentation, what you require to do, you require to know the step size, means where you will go for the next experiment. So, there you will be guided through the process variables and their corresponding regression coefficient values. You start with one of the process variables and the chosen process variable is one, where you have maximum knowledge about that variable, or that variable has the maximum amount of contribution towards the response values. Okay. So, with this background, we will start this example where there are two process variables. One process variable is x1 is, suppose the xi1 is reaction time, and your xi2 is your reaction temperature, and the response variable is process yield, variable y is process yield. Okay. Suppose you are operating with reaction time maybe at 35 minutes and this with 155 degree Fahrenheit. What does it mean? It means that you are working with two process variable, one is your reaction time, that is xi1, and your one is reaction time and second one is reaction temperature. So, reaction temperature xi2, and you are operating maybe in this zone where reaction time, the center point in this zone is this one equal to, I told you that 35 and this one equal to 155. So, that when this may be, we can say this is 30 minutes, 40 minutes, then this is maybe 150 Fahrenheit and 160 Fahrenheit. This is the current operating zone, and your average yield on an average yield here is 40%, which is very less. So, you want to improve it, find out where it is the maximum. So, in order to do so, you have to start experimenting here. So, what kind of experimental design you adopt here? So, you all know that 2 to the power k design can be adopted here. So, 2 to the power k factorial design is very much known to you. Suppose if we create for reaction time high and low, for reaction temperature also high and low, and if we assume that reaction time high is 40 minute and low is 30 minute, and here low means 150 and high means 160 degree Fahrenheit, then you got the 4 factorial points. In addition, because if you have 2 factors and their interactions and all those things we have seen earlier also, that if you go for 4, you have to go for replications to get the estimates of the effects. In addition, you have seen if you have the center point, then at the corners you may not, the factorial point you may not do replication, but at the center point if you do more replications, what happen, using center point which is devoid of basically which is the maybe the current which is the current operating zone, where if you conduct more number of experiment you will be able to get the error terms to be estimated, even if you go for one experiment each at a single replica at the corner points. That is what you have seen in 2 to the power k factorial design. So, that means here it is basically that factorial design with center points. So, 2 to the power k factorial design with center points, with center point. Okay. So, what more you require to know, this will be converted to coded variable x 1 and this will be converted to coded variable x 2. So, from that means high will be your plus 1, low will be minus 1, similarly here high will be plus 1, low will be minus 1. So, this is related to x 2 and this is related to x 1. So, we have discussed this issue how to convert the original variable to coded and coded to original variable. So, I am not going to discuss further. So, suppose under the situation the design matrix is like this x 1 x 2 minus 1 minus 1 minus 1 plus 1 plus minus, these are the factorial points and the center point 0 0, because you know that plus 1 minus 1. So, obviously, this point will be 0 0 x and y respect. So, the central point is 0 0 and if you have conducted experiment and let the responses are like this. So, what is your aim? You want to fit a first order model. So, you see the coded variables from the original variables and first order model is fitted here. What is first order model? Y equal to 40.44, y equal to 40.44 plus 0.775 x 1 plus 0.325 x 2, that is y cap. So, then what is this one? This is basically average of all y observations. Well, how do you get the x 1? X 1 you get, that means the sorry beta, this is beta 1, this value how do you get? This is beta 1 cap. How do you get? This is basically 1 by 2 into effect. So, how do you get the effect here? Effect you get average. So, 1 by 2 y, suppose if I say this is x 1. So, x 1 plus bar minus y x 1 minus bar in this way, and you know how to compute the effects. So, similarly, this one. So, and the regression coefficients will be half of the effect values, that is what you know. So, accordingly this is done. Other way you can create the beta cap equal to here beta 0 cap, beta 1 cap, beta 2 cap, straight away going for regression x transpose x inverse x transpose y, and where the data are given in the previous slide. Okay. Now, this is the first order model what you have fit. So, y cap is the expected value of y for different combination of x1 and x2. So, what you have to do now, that you have to check whether the first order model is really a fitted one at this current operating condition or not. So, in order to check whether it is fitted or not, what are the things you have to do? First, you have to find out the error estimate. Second, you check the interactions. Third, you check the quadratic effects. So, what are the things you have to check point for first order model? Checks. One, you estimate the error terms, errors. Second one, you basically test for interactions, and third one is test for quadratic effect. So, in order to test all those things, estimate of error is very important. Estimate of error will be done using the central point data on central point or central point observations. Test for interaction means in this particular model, first order model, that you have considered like this, that y cap equal to beta 0 cap plus beta 1 cap x1 plus beta 2 cap x2, but there can be beta 1 2 cap x1 and x2. So, that is means beta 1 2 cap whether it is significant or not. And when we are talking about quadratic effect, you may add something like this beta 1 1 x1 square plus beta 2 2 x2 square this cap. So, that means you want to test here that beta 1 1 cap plus beta 2 2 cap whether they are significant or not. So, if you find that this is equal to 0 or this equal to 0, this test is accepted, then you consider the first order model. If you find that this and these two are not accepted, that this hypothesis beta 1 to 0 and this is not accepted, so this model is not valid, what you require to do? You have to add these points there. Okay, these effects to be considered, and it may so happen that that is a local minimum, local optimum situation, or then you have to go you have to do separately further experiments in other zone and then do it. Okay. So, one after another we will now go for all the first one is estimation of error. So, estimation of error. Okay, estimation of error, we will say sigma, this is the meaning. What you do? You will use the central point, send data, use data on what data? Y data on center point you write. So, what is the y data on center point? Where x1, x2 coded values are 0. How many data points are there? 40.3, 40.5, 40.7, 40.2, 40.6. Okay. So, using this data, can you not find out the sigma square? Yes, you find out the mean of this data, deviation from the mean, and then square divided by how many data points? 5 data points are there, you will find out. Other way, that sigma square in general this will be square all the data points minus the average square by 5 divided by 4. Using this formula, so that means 40.3 square plus this square plus like this plus 40.6 square minus 202.3 square by 5. If you add them up, it is basically 202.3. This square by 5 divided by how many observation? 4, 5 minus 1, 4. This will give you 0.0430. So, this is the estimation of error. This is basically mean square error. Okay. So, when we have discussed central point, that one we have already seen this one. Now, what you want to do now? You want to find out the second one. Second one is your beta 1 2, that effect is there or not. So, hypothesis is H0 beta 1 2 equal to 0, null hypothesis beta 1 2 not equal to 0. So, beta 1 2 how do you find out? You will find out from the factorial points. So, what are the factorial points values at low and high? So, when both at low mean this point it is 39.3, when your first one is high value. So, x1 at high this is 41.5, no 40.9, when x2 high this is 40 and x1 this, and both at high 41.5. So, the interaction effects will be both similar and both the average of this plus this by 2 minus average, that means this plus this by 2 will give you the interaction effects. So, interaction effects will be accordingly, you see that what happened, or other way you know the contrast, So, you please see this factorial points. So, -1 that will be +1, contrast for x1 x2 contrast will be, that means +1 then -1 then -1 then +1. Once you know this contrast, so effect will be contrast divided by 1 2 into contrast by n. N is the total number of observations. Okay. So, so using this contrast or the other way these two, so see what is happening, 1/4 of this. So, 39, 41, 40 and this will give you that 1/4 into this, because you are basically, what is your contrast? Contrast is this one in between, and you are estimating the regression coefficient, means effect by 2, that is why instead of 1/2 it is 1/4. So, beta 1 2 is your 0. Beta 1 2 cap is minus 0.025. Okay. So, as I told you, what is happening, first you find out the effect 41.5 plus 39.5 divided by 2 minus 40.9 plus 40 divided by 2, that will give you the interaction effects AB. So, using this data you can find out AB equal to half of 41.5 plus 39.3 minus 40.9 minus 40, then beta 1 2 will be half of AB, that means 1/4 of this. Now, in between this quantity is minus 0.10. So, beta 1 2 is minus 0.025. So, this quantity is, what is the degree of freedom for this? Degree of freedom is 1. And what is the MAC error degrees of freedom? You got MAC value is 0.043 and degree of freedom is for this equal to 4. Okay. So, now you know that whether this value is significant or not, just compare this with your MAC. Okay. So, you find out. Achha, now what happened? In order to get F, you require to find out SS, that AB or x1 x2 divided by degree of freedom by MSE. So, SS how do you find out? You know the contrast, so contrast square divided by 4, that will give you SS interactions. You just see here. So, contrast square by 4 is the interaction, SS interaction, F SS interaction by 1 and sigma square, that you are getting 0025 by 043, this is 058. So, this value is your 0.0025 divided by 0.058. So, how much it is? Sorry, 0.043. So, this is 0.058. 0.058. Okay. Now, this value if you compare what is the with F1 I think 4 0.05, then you will find out this value is much higher than this. So, ultimately that means this effect is insignificant. Fine. So, interaction effect is not there, interaction effect is negligible, that is what you have done here. Now, go to quadratic effect. So, if you recall that we have discussed that if there is center point and if there is no quadratic effect, then the average, when you develop the response surface, the average on the center points and average at the corner factorial point, they will be same, ideal case, the difference will be 0. So, that is the case. That means, if there is quadratic effect like beta 11 plus beta 22 in this case, so that will be represented by your y factorial point minus y at center point. Okay. Now, y bar at factorial point is 40.425 and y bar a center point is 40.46. This value is minus 0.035. Okay. So, what you are doing here? You are creating a null hypothesis that beta 11 plus beta 22 equal to 0. Alternate hypothesis is beta 11 plus beta 22 not equal to 0. So, what you require to do now? You have to, in order to conduct F test, you require to know SS pure quadratic divided by obviously your that sigma square, that is MSE. So, this is the computer. Now, how do you get SS pure quadratic? If you recall that SS pure quadratic, we said that number of points at the factorial points into number of points at the center into y, then y f bar minus y c bar its square divided by n f plus n c, and it has 1 degree of freedom divided by your MSE. Now, how many points are there at the factor point is 4, center point is 5. Now, y f bar minus y c bar is this. So, minus 0.035 square divided by MSE sigma square is 0.0430. So, this value is coming around 0. Okay, this divided by NF plus NC is 9. So, this value is coming around 0.063, which is again much less than that F114 0.05. So, quadratic effect is negligible. So, you got that you factorial point design with center point has given you to estimate the error, given you data to estimate the error, you have estimated the error, you are in a position to find out whether the beta 1 that interaction effect is significant or not. you are also in a position to find out that whether that quadratic effect is present or not. Fine. So, quadratic effect is not there, interaction is not there, that means the first order model is probably a fit one. Okay. But what you require further, that means we are saying y cap equal to beta 1 cap x 1, let it be beta 0 cap plus beta 1 cap x 1 plus beta 2 cap x 2. This is a fit one. But whether these values, the beta cap, they are significant or not, parameter estimates, test of parameter estimate you have to do, test of parameter estimates. So, what you require to do? You require to find out the variance of beta I. Okay. So, if you do not do this, then you will not be able to, you have the estimated value, but variance you have to find out. So, if you can recall that when we talk about optimality issues in factorial design, there we said that under this factorial design case, the variability part is basically MAC by 4. Here basically 2 to the power 2 design, so MAC by 4. So, then standard error of beta I you have to find out, this is MAC square root of MAC by 4. Because of this coding, so you got that for all the variables are -1 to +1. So, the standard error of beta I will be equal for all the all the coded variable, and this is nothing but 0.0430 by 4 square, which is 0.10. Now, if you see what is the estimate value, the regression coefficient value, this is 40.44 plus 0.775 x 1 plus 0.325 x 2. So, with reference to the estimated value, the standard error is very low, and using t test you will find out that they are significant. So, first order model is fit. Okay. So, first order model is fit. Now, this is what is your ANOVA table. I will not discuss further ANOVA, because you all know ANOVA model is significant and residual is this much, and there are interaction insignificant, pure quadratic insignificant, and pure error is 1720, that you have seen also earlier. So, total is this, and this ANOVA table also giving the support to the first order model is fit. Once first order model is fit, you got the direction. Now, how do you set the direction? The direction you see this side, start with coded variable. In coded variable, origin is 0 0, and you have your in natural variable, that is 35 and 155. So, you choose step size delta for which one, for the first x 1 or x 2. We are choosing x 1 here because x 1 is having the maximum contribution compared to better contributor than x 2. So, now what will be the step size? Step size, if you want to find out for x 1, then you have to go to the natural values, that 35 is the starting point. Now, from process knowledge, you have to find out whether the next experiment you will conduct at 35 plus 5 or 35 plus delta x 1 basically. So, through process knowledge led, it is 5. So, that means delta x 1 is 5. If delta x 1 is 5, then what will be the delta x 2 value? That will be guided by the regression coefficient. What is this? Let us go for the this. Okay. So, this is the basically the steps. So, you start with origin, then step 1, choose step size for one of the process variable, say x j. Which one you will choose? Has been known the most or has the largest contribution in terms of effects. Then step size will be delta x I, then you will choose this one. Once you choose this one, delta x j, the next variable step size will be beta I, the estimate of that value divided by that estimate of the chosen one and by its step size. Okay. For example, in this case what we have chosen? We have chosen that x 1 is 1, delta x 1 is 1 and step size for that variable is 5 units. Then for the x 2 it is basically beta 2 by beta 1 by delta x 1 point, and beta 2 is 0.325 and beta 1 is 0.775 by 1. So, this is 0.42. So, what is your step size for x 1 is 1 and step size for x 2 is 0.42. Okay. So, you see that in the slide what happened, we are changing delta, we have fixed in coded units and in natural units. Now, origin plus delta, origin is 0. So, this is coded unit and this is in the natural units, and you conduct the experiment and your response value is this, followed by the second step will be 2. So, that means 1 coded variable 1, 2, 3, this way you are changing, x 2 you are changing accordingly 0.42, 0.484 like this, and the resultant natural values is required, because actually when you do the experiment you have to set the process parameters according to these values, and then after the experiment you will get the y value, and this is the case. So, this is the way the sequential experiment is conducted, and the algorithm is also the what I have given you, that is the algorithm for conducting the steepest ascent from the first order model. Okay. Then if you plot this, what you are finding out at the 10th step, this is the maximum value. So, that means you gone to the new position. What is this new position? New position is you started with 35, 155, 35 and 155, you have gone to this place as 85 and your 175, the center point, center values. You started experimenting here, your first order regression will lead you to there. Now, why here is the curvature, along this line point you now experiment. So, along 175 and 85 175 you do the another experiment. Okay. So, what you have done now, then you are here, now you are doing another experiment. Again the center point is 85 175 and the factorial points are 80 to 90 and 170 to 180. Here it was 30 to 40, then this is 150 to 160. Your movement, you have that improvement path reached here 80 to 90 and then 170 to 180. Here you have used factorial experiment with center point. That means this is the case. So, factorial experiment with center point here. Here also you do factorial experiment with central point. So, that means you are going from here to here. Okay. Factorial experiment with center point, and then so 80 170, and this is what in the coded design is this. Okay. So, once you do experiment, you are getting the response values like this. So, what you to do here now, at this new location you just see whether the first order model is fit or not. So, how we are doing this? You do exactly the same thing what we have done here. First here find out the estimate the error. Okay. Then second you find out that test beta 1 2 equal to 0 or not. Then test beta 1 1 plus beta 2 2 equal to 0 or not, and then test whether beta 1 beta 2 are significant or not. Exactly same manner the way you have fitted first order model. So, here you fitted first order model, here also you fit first order model. Okay. and then what you will find out that from the diagram we are seeing that the things are going like this, then here and reducing. So, there is in this zone there is quadratic effect. So, it is expected that first order model will not fit, but you have to test, there is no because if the zone is very large one, you have taken a large zone, then what will happen, maybe first order model is actually fit there. So, whatever may be the case, so you have to again feed the first order model and the result is given here. Okay. So, you see that although interaction is insignificant, but pure quadratic is significant. So, that means first order model is not fit in the new operating zone. The finding says the interaction and pure quadratic checks imply that the first order model is not an adequate approximation. The curvature and in the true surface may indicate that we are near optimum, but you do not know whether you are near. First order model helps you go to the new operating zone, and there when you after experiment you found out that first order model is not fit because quadratic effect is there. So, what you have to do now, you at this new zone you have to fit a second order model and then see that whether second order model is fit or not. Okay. So, whether if it is the quadratic effect is there, if it is second order polynomial, then you will get the optimum value there. Okay. So, let me conclude. So, ultimately you know that we have basically presented here the some portion of the chapter 11 by design and analysis of experiment of Montgomery, and in a nutshell what we have discussed so far. We says that response surface methodology is very useful one, and it is heavily used to find out the optimum zone of operation. Here response surface methodology actually rely on regression. There will be first order regression, there will be second order regression. We have discussed so far the first order model, and there what we have shown that with reference to one example with two factors, we have shown that how you will fit the first order model, what are the conditions, and then how do you do using the first order regression data, first order model data, how you go for sequential experimentation, and then how do you find out the step size, conduct experiment, then change this one after another, and finally you will get some plot like this. Suppose this is the point of optimum. Now, you have to again do another experiment from here to here, and this experiment you feed the first order model again. If first order model is likely to be unfit here, but if it is first order model is fit, again use that first order model, go for maybe another domain of operating zone or another range for operating zones. So, this is what is our first order model for response surface methodology. Next class we will discuss second order model for RSM. Thank you very much.